If you ask around what are the real numbers, most people will tell you, okay, so the real numbers are the rational numbers and the irrational numbers. And that's enough for most people, or at least for many years before we actually learn, right? But if you look closely here, rational numbers, we know what they are. These are ratios of integer numbers, okay? And they are well defined. We define them in terms of integer numbers. And then when we want to look into the rational numbers and we ask, okay, what is an irrational number? Most people will define irrational numbers as the ones that are not rational. Okay, but you see the trick there? The ones what? You see, when you say the ones that are not rational, here what you are implicitly assuming the real numbers already. Okay, so here you are using, here the definition uses the defined, if you see what I mean. When you say the ones that are not rational, you are implicitly referring to a framework of real numbers, okay? Because the ones are, they have to exist somewhere, okay? But this is a catch, okay? So the definition becomes circular and that's not acceptable. So for this, we actually need to pay a lot of attention because we already know numbers like a square root of 2 or pi or phi that we have been using for years, and we know they are not rational. Okay. So then, when mathematicians started to give some grounding to all the theory that existed in the 19th century, they realized that they needed to provide a construction of what real numbers actually were, because it was not clear. It was a bit mysterious. It's like something that is added to the rationals, but in a not very clear way. So let's put some order in that mess. Okay, so what they did is, since we already know the rational numbers, and somehow the irrational numbers seem to be mixed up with the rational, they come intertwined. Maybe we can construct the rational numbers, or if you want, all the real numbers from the rational. Okay, so this is what two mathematicians did, Dedekind and Cantor. So they constructed the real numbers from the rational numbers in two ways. The first one is using Dedekind's cuts, and the second one is using equivalence classes of Cauchy sequences, and this one is due to Cantor. Okay, we will see about Cauchy sequences in a couple of weeks or three. For now, we are not going to use that. We are going to, well, the proof that you see in the book is using Dedekind's cuts. So we will discuss a little bit how that is done, but without going in full detail. Both of these, this is relatively recent. I mean, real numbers, we are talking about numbers, right? But this was done, both of them in 1872. So that's 19th century, okay? And people have been using irrational numbers ever since the ancient Greeks. So you see that it's relatively recent to want to give foundation to what we know. Okay, so let me just write here, before we get into any further detail, what is the fundamental theorem here. The theorem says that there exists an ordered field R, okay, which has the least upper bounds property. Okay, this is the field of the real numbers, and there's a second part. Moreover, R contains Q, the rational numbers, as a subfield. Okay, so this is in this way we can close the question. With this we know that there is an ordered field that has the properties that we desire. It contains the rationals, it's an ordered field, and it has the least upper bound property. Okay. The second part, saying that contains Q as a subfield, this is important because this means that we can do operations as usual. Okay. The operations of addition and multiplication when applied to members of Q are as usual. All right. So the proof of this theorem, it's actually quite, it's long and it's a bit tedious. So we are going to just see what are the main ideas, but we will not get into full detail. If anybody wants to see the details of the proof, it's on the appendix to chapter 1 in the book, okay? So let's just, in this case, discuss the main ideas. Okay, so that we know what was done, and that will be enough. So this is going to use, the proof we are going to discuss now uses Dedekind's cuts. Okay. So what are Dedekind's cuts? So these are so this is the way we, okay, let me rearrange things here. This is the way we are going to define the real numbers. Okay. The members of R are subsets of the rationals called cuts. Okay, and what is a cut? Well, it's basically what it looks like. So if we have here our rational numbers, this line looks solid, but it's not, okay? Because it's only the rationals. It has, it's porous, it's like a mosquito net. Okay, so a cut, we are just going to split the set of the rational numbers in two parts. Okay, two halves, and those will be the cut. Okay, so cuts split Q into two halves, okay? So we have two sides. Let's say we have a number alpha where we do the cut. Let's call it, yeah, alpha is good. So on one side of alpha, we have all the rational numbers that are less than alpha. And on the other side, we have everything that is bigger. All rationals bigger than alpha. Okay. So here, this, by the way, this looks like a finite interval, but it goes all the way, okay? So we have the two cuts would be up to alpha and then from alpha. So here the important point, whoops, I went to yellow. So the important point is that for every cut that we make, we have a correspondence between these partitions and the real numbers. Let me put everything in the same line. Correspondence between these partitions and real numbers. So basically, every real number gives you a partition. It's just a choice of where to split. Okay. So here we have two options. Maybe we partition in a rational number. Okay, so rational numbers correspond to partitions that contain a largest member. Okay, let's say we partition in negative infinity 1/2, and then 1/2 all the way. Okay, so you see that here it's included in the cut. You can leave it on the left or on the right. Usually you leave it on the left, but it's included in one of the two sides. And then the irrational numbers okay, these ones correspond to partitions with no largest member, okay? So for example, if before we had 1/2, now we can look into, let's say, square root of 2, because we always say that one. So in this case, you have the two pieces of rational numbers. Okay, this would be your set A, this would be your set B, and these are sets of the rational numbers. Okay, and you see what happened there. We are cutting on an irrational, so we can get as close as we want with rational numbers to the extreme of the interval, but there is no largest member in the interval. Okay, so what have we done so far? So we have replaced the real numbers that some were well defined, some were not. We have replaced them by these sets called cuts that are subsets of the rational numbers. So then these are things that are well defined. Okay. And then the rest of the proof, which is the part that is longer, okay, consists on defining the operations for the cats, okay. Wait, that comes after. Sorry, first thing we need to do is check that R defined like this is an ordered field. With the least upper bound property, okay. And then we define operations for cats, okay, and we need to check the field actions that we saw last week. And that's it. This is basically the idea of the proof. It's several pages. It's on the book. We are not going to see all the details, but you see the main ideas here is to replace the notion of number that we have as a point in a line, replace it by cats, by partitions of the rational numbers. Okay, very important, of the rational numbers. And then once we have a good definition of numbers, we need to define how to check that it's an ordered field, that it satisfies the least upper bound, define the operations for the numbers as we have constructed them, and then check the field actions, and then we are done. Okay, what makes this work is the fact that the rationals are ordered and they are dense. Dense means, we will see more about this in the next video, but dense means that between any two real numbers, there is always a rational one, okay? Any two real, there is always a rational in between. And between any two rational numbers, there is this property that we saw, that you can always find another rational number in between. Okay, those are the two things that make this work.